Alright. Medium problem, convert sorted list to binary search tree. Not seen it before. Let's read the question. Given the head of a singly linked list, ascending order, height balance, binary search tree. So binary search trees, they have all the left children are smaller than the value of the root node, and then that is smaller than the values of all the right children. And we want it to be height balanced. Okay, so we have a linked list. Okay, so we want to find the middle node of the linked list to be the root, because we want it to be height balanced, and then we want to continue to do this on the left and right side. So I'm thinking recursive. We could do this recursively if we find the middle node and then we recurse on the left side, again finding the middle node. But we have a linked list, so we cannot just use index to just find the middle node. Well, I guess we could index it, but that would require traversing through the linked list again and again, which is very inefficient. How could we avoid traversing the linked list again and again? Well, okay, so if we had two pointers, one fast, one slow, we could do the fast pointer 2 times, so we would end up with a slow pointer in the middle and fast at the end. That's how we find the middle of the linked list with 2 pointers. And once we found that, I guess we could just do that again. So for the left part, we're gonna need another pointer going from the left and now the end is where the last middle node is pointing. For the red part, we are doing that as well. Well, that should in theory work, but that is traversing through the linked list again. Definitely not efficient. Or, I mean, could we do better? Well, I guess we could also just traverse the linked list once and then just store it in an array, and then we can just use the indices from the array to find the middle node instead of traversing the linked list again and again. I guess that would be way more efficient. Okay, let's do that. Okay, let's have an int array. Let's call it input. And how many elements do we need? We will need to traverse. Well, we don't need an array. We can do a list. Then we could just do this once. A new list of int, and then while we're traversing, we are gonna add every value to the list. Okay, let's do that. Do we want to save the head node or just use that? Probably don't need it for now. Okay. Because we want to return the middle node. Alright, we're gonna sacrifice that. So while head is not null, we are gonna do list add head value, and then head is head next. So we're gonna be adding 1, 2, 3, 4, 5, all of them to the list, and at the last one we're standing here adding that, and then head is head next. That's pointing to null, so that's when the while loop stops. And now we have a list of all the values. We just need to convert this list to a binary search tree using an index to point to the middle one, and then recurse on the left part and the right part. Okay. We need a helper function. Let's call that convert to BST. We are gonna pass in our list, and we need index left and right. Let's go with left and right. So we are gonna do mid is okay, left plus right. Well, do we need the root node to be there? Okay, tree node root is gonna be a new tree node with value of the middle node. Root left, it's gonna be convert to BST list of left to mid -1. right is gonna be and we want to return this root. So if we imagine now this is just a list, not a single linked list anymore, so we have a list of integers, then we find mid, which is left, right? So return, convert to BST list 0 and list count -1. So we have count is 5, so 0, 4, left is 0, right is 4, mid is 2, so root will be a new tree node with value at index 2, which is 0. Okay, then root left will be whatever that's returned to the left part of this, which is left until mid -1. So mid is currently 2, left is 0, mid -1 is 1, so we have this will be list 0, 1. And the right part will be list mid is currently 2, so list 3, 4. So this should be handling this part, and it should return the root of that part. So what happens when we go in here? So we have list 0, 1. Okay, list 0, 1. Mid is 0 again. New tree node will have a value of -10. Not -3. Okay, so 0 left would have a value of -10 here, and that -10 left would be, so that's 0, mid is also 0, so that will be list 0 -1, so if left is bigger than right, we should return a null. So if we have list 0 -1 -10 here, the left node of that should be null, and the right node of that should be we had mid was 0, so that would be 1, 1. Okay, 1, 1. We're going there. List 1, 1. Mid is 1. New tree node is with the value -3, so we have -10 here, and then that right would be -3. And what happens after that? So that has -3, 1, 1, and then 1, 0, return null. 2, 1, return null. Okay, so we have 0, -3, no, 0, -10, -3, nothing there, null there, everything else is null as well. And then the right side would be similar, there will be mid, Although since we are doing mid this way, so it will always be going towards the smaller node if left is just one less than right. The mid will always end up to be equal to left, so the next root node to be connected will always be the smaller value one. So it will be 0, minus 10, minus 3, and then 0, 5, 9. Okay. Let's see if it works. Okay, seems to work. Yeah. Okay, great. Let's see, we have. So what we were doing was to first traverse the linked list and store everything in the list. And then we have a helper function to recursively find the middle node to be the root node to return, and then also recursively do the left and right children in the same way. Yes, okay, so let's see, anything, no follow-up here. Related topics, linked list, divide and conquer, tree, binary search tree, binary tree. Similar questions. Okay, so time for time and space complexity analysis. Let's see. Time complexity. So this part, we are just traversing the linked list once and store it at the same time. So that will be O of n, where n is the number of input in the number of nodes in the original linked list. So that's O of n. Let's see the recursive function. What will be the time complexity? So we have that as a list. We find the middle one right away, create a tree node, and then we recurse on the left. We go to the left, also find the middle node, and then we keep recursing. So what would be the time complexity? What if we had 3 nodes here? So we first go in there, and now we recurse on this part. We have 3 again. We would just find the middle node right away, and then we recurse. Seems to me that it is O of n, unless I'm missing something. It's always a bit tricky to analyze time and space complexity for recursive functions because they will be like stacking up. All these recursive calls will be stacking up in memory. Wait, is it in the? It should be in the. Oh, now I need to look it up. Is it in the heap or in the stack? It's gotta be in the heap. Okay, I have to look this up. Okay. I'm not completely sure, but I think the time complexity should be linear O of n. And space, we are also using linear to store in the list, and then we are recursively building this tree, so I guess that's linear again. Okay, let's see if it's right, if it's correct. Let's look at the first one. Oh, okay. Slow and fast. Oh wow, they are using 2 pointers instead of storing in the list like I did. Okay. Oh, okay, let's see. Head, slow next, tail. Yeah, that was my first idea. So this is the implementation of my first idea with the 2 pointers, one going double as fast. So when we do this, but this was doing exactly what I was thinking that would be inefficient. Right, this is not efficient. Since you have to traverse the sublist in each recursive call, yeah, that's exactly what I was thinking. Okay, seems like no one is converting the linked list to a list first. Everyone is traversing. Okay, am I missing something? Did it say somewhere that we cannot convert to a list? Convert to a tree. Okay. Constant space, linear time. Okay. Okay, so we traverse the linked list once to get the count. And now we're doing mid. Left. Right. So why would this be linear time? Node. Wait. Why am I not seeing this node? Okay, there's a global variable called node. Okay, which is set to head. Okay. I think I will need to look more to understand this solution. Yeah, so it's not constant space because it's recursive. Okay. Okay, I think I'm gonna come back to this later tonight to understand it fully, so I can stop here for now. Okay. Since apparently there is a linear solution without using an extra data structure to store all the values, which is really cool. Okay, so that's it for this problem. I'll see you in the next one. Bye.